I'm Zhang. I will present our work, EdgeBalance, module-based load balancing for network edge data planes. This is a collaboration with AT&T Lab Research, my mentor Abhigyan, and my advisor team when I was a student at George Washington University. I will start from background and motivation. Today's cellular networks separate the control plane, which manages aspects like routing and billing, and from the user plane, which handles each device's data paths. This separation allows operators a more flexible deployment and dimensioning of the network. However, the typical deployment model still keeps both of the services mostly centralized. Thus, a large geographic region may have many cellular access points, all connected to a single user plane and control plane. As we move to the 5G era with support for high data rates and low latency computation, more services will be pushed to the network edge. This change means that future cellular design includes a distributed user plane. By moving the user plane to the edge, it becomes possible for the network operator to deploy specialized network services in the data plane, which closest to the user. The user plane at the edge can then act on customers' flows and provide a variety of services to them. A flow typically goes through a sequence of network functions like here the figure shows, which forms a service chain. These network services are often very latency and throughput sensitive. When traffic rates arise, network services must be replicated to avoid any instance becoming the bottleneck. As a result, a load balancer is needed to dispatch the flows across the replicated services and evenly balance the load to efficiently use the distributed resources. There is much existing work on cloud load balancers, such as Google Microsoft Load Balancer, Facebook MC Router for memcached services, and Twitter 2M proxy. But these kinds of load balancers are designed for homogeneous services. They usually leverage static policies to choose a backend server and rely on a consistent hash or similar algorithm to maintain flow affinity. In EdgeBalance, we want to build a load balancer for network function service chains. These network functions are deployed as mid-boxes. There are several important differences in how the load balancers need to be designed compared to existing solutions. The first challenge arises due to the mid-box nature of network functions. For network functions to operate correctly, the same replica instance needs to handle both directions of the flow. This is not always the case with cloud load balancers. For example, sometimes it is possible for requests returning from a server to bypass the load balancer and go directly to the client. Bidirectional flow affinity means that we must ensure both directions go through the same replica instance. Guaranteeing this becomes challenging when you consider the network functions can modify the headers of packets flowing through them. Thus, a load balancer must be stateful and able to count for network functions that update portions of the header, such as NAT functions. The nature of edge data centers also make load balancing harder compared to traditional cloud environment. Edge data centers are much smaller, meaning that resources need to be used as efficiently as possible, and being able to dynamically scale up and down is critical. As discussed in other talks in this workshop, an edge might also use server heterogeneity to provide more flexible trade-offs for performance, power, and cost. The service chains themselves are also may be heterogeneous, with varying processing costs at each node. Finally, the incoming network workloads may vary, with a mixture of lightweight mice flows and heavyweight elephant flows. In such a dynamic heterogeneous environment, simple static load balancing policies are not effective. Dynamic load balancing is needed, but once again, the nature of network functions makes it harder. And more challenge. Fine-grained metrics such as CPU utilization is needed to guide such a load balancer, but the way network functions are implemented prevents this to be easily gathered. Most high-performance network functions rely on pool-mode I/O frameworks, such as DPDK, but this makes getting accurate CPU usage measurements difficult, since the load will appear to be 100% no matter what the workload is arriving to the system. Further, the monitored metrics may bring the stale data and increase the system overhead because of the cost to collect and transmit from the servers to the load balancer through the network fabric path. Now I will talk about our system design. Motivated by the above problems and challenges, we designed EdgeBalance system to have not only high performance, but also provide bidirectional affinity, use a module to accurately predict the CPU and then dynamically guide load balancing. Next, we will describe some key components in the system. To guarantee bidirectional affinity, EdgeBalance maintains both forward and reverse flow tables. A forward flow is inserted into flow table. Forward flow table when a first packet arrives from the source. At the same time, a reverse flow is added into the reverse flow table. However, if a network function changes the packet header, an update flag is added into the packet header. This flag sets the load balancer detect the change, so it can update the flow entries accordingly. When a flow ends, EdgeBalance will remove the forward and reverse flows at the same time. Trying to maintain up-to-date monitoring data is difficult due to the polling problem mentioned earlier and the issue of data going stale. In EdgeBalance, we take another view to be aware of the CPU load. We know that the CPU load on a server is related to the chain processing cost, the number of flows, and the flow rate. Therefore, we use this information to build a model to predict the CPU usage. The load balancer needs to gather some statistics about packet arrival rates, but there may be millions of flows through the same system. Maintaining per flow states for prediction will not be scalable. Instead, we use a much smaller data structure to track the number of packets and the number of bits for a host, a core, and a chain. The number of hosts, cores, and chains are limited relative to the number of flows, which can make the tracking much more scalable. EdgeBalance uses a PID controller to dynamically adjust the weights used to balance the load. The controller is designed to try to evenly balance the predicted CPU load across all CPU cores. It sets even CPU usage as the optimization target, and then compares the predicted CPU against it to dynamically adjust the weights and dispatch the flows. As we show in our evaluation, this allows the controller to quickly converge on the right weights without requiring detailed monitoring on each host. EdgeBalance is implemented using high-performance networking technologies, so it can operate at millions of packets per second. We use DPDK for fast network I/O, so that all of the packets bypass the kernel, avoiding the expensive packet copy between the user space and kernel space. It is NUMA-aware. With multiple threads, we use receive-side scaling to dispatch the flows into different NIC queues, and each queue is only polled by one thread. Each core has its own thread and the flow table to eliminate contention on shared data structures. Each thread will periodically clean up the spider flows to free memory space. These features make the system lockless and highly scalable. Let's see some evaluation results. We did the experiment on the NSF Cloud Lab with 10 gig support, use DPDK packaging to generate the long flows and T-Rex to generate the short flows. Use BAS as a data plane to run the network functions, which is open source from Berkeley. We first evaluated the accuracy of a CPU prediction model with varying processing cost and compare against the predicted CPU and measured CPU. We can see the predicted CPU is aligned to the measured CPU. At the same time, we also measure different number of flows and flow rate to see the accuracy. Next, we send mixed elephant and mice flows to measure the throughput and the latency of different approaches. For the monitor case, we instrument BAS to measure the real CPU usage and periodically report it to the load balancer to adjust its weight. In the experiment, we keep the overall send traffic the same, but increase the elephant flow ratio. EdgeBalance outperforms both static and monitor-based load balances. In summary, we have shown that load balancing for high-performance network services at the edge has several important challenges not seen in normal cloud load balancing. We developed EdgeBalance to manage the load for network service chains at the edge. It provides bidirectional flow affinity, which can ensure the forward and the reverse flows go through the same set of network functions, even if the packet header might get changed along the way. The system supports dynamic load balancing, but accurately predicting the load with module, we use a PID controller to dynamically adjust the weights to evenly balance the load. That's for my presentation. Thanks. If you have any questions, feel free to reach out to me. Thank you.